Okay, so isomers are, so we got structural isomers, and we're also going to look at bond energies as well, so how to break bonds and stuff like that. But to start off with isomers, pretty much the deal is isomers have the same formula, but a different structure. So if you notice, the formula for this first one here on the right is C3H8O. Okay? Then we have C3H8O. Right here. Wherever there is wherever they're crossing, I'm sorry, wherever there is a cross and wherever two lines intersect, it's just understood that there's a C there. Sorry. My bad. There you go. Okay, there's C, that C's there. Wait, hang on. Did I miscount these? 2, 4, 6, 8. No, it's good. All right, so 2, 4, 6, 8 hydrogens. All right, so then the last one here, 2, 4, 6, 8. Oh, okay. So see how each one of these molecules are the same formula, all right? Same formula, but we have different, we do not have the same structures, okay? Different structures. And what happens there is the properties, because of the different structures, right? Each molecule has different properties. All right, because if you look at, like, let's say these three molecules right here, two of these are a lot more similar than the third one. I mean, if you think about intermolecular forces that could be present in each one of these, okay, well, each one of these molecules, right, are polar. Okay, each one of these are polar. They're asymmetrical, right? So they can have polar-polar, dipole-dipole interactions with one another. But this guy here has an H that's attached to an oxygen. This one has an H attached to an oxygen as well. You can have hydrogen bonding there. That hydrogen can do hydrogen bonding. Okay? So these two guys can do hydrogen bonding. However, this molecule, while it is polar, it cannot do hydrogen bonding because that hydrogen is not connected to that oxygen. All right? So these guys might have similar boiling points, melting points. This one will be very different. Have different properties, okay, because the structures are different. So this is the idea. An isomer, same formula, different structure. So for example, right down below here, we got propanoic acid and methyl NO8. All right, these guys both have C3H, what's that, 7? O2. H6, thank you. Here we go, H6O2. All right, propanoic acid is one of the products of breaking down fatty acids in your body. Okay, you'll make propanoic acid. Methyl NO8, that's like used to it's used in things like acetone, but also used to be used when we actually had film, like Kodak film, right, to help develop film and things like that. Okay, slightly toxic. All right, where the propanoic acid, no problem. It's in your body. It's made. It's one of the products of breaking down fatty acids. Okay, triglycerides and things like that. Okay, so same formula, very different properties. Structural isomers of one another. All right. Okay, so let's try and draw a few isomers. Okay, let's try and draw some isomers. So we've got a chain here of pentane. Okay, this guy is what is that? C5H246 plus 6 is 12. H12. Okay, so we want to draw some structural isomers. I'm not going to draw in all the hydrogens here. I'm just going to put in some lines. Okay, so let's say I do this. 1, 2, 3, 4, 5. And then there's 3, 6, 9, 12 hydrogens there. That's an isomer. So would this. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like that's an isomer as well. All right, what's an example of one that we can draw that's not an isomer? What if I drew it like this? This is not an example of an isomer. It's the same as the structure that we started with. Okay? It's the same as this one right here. Right? Even though I just drew that carbon like coming up out of that one, this is still CH2. So is this right here. That fourth carbon still CH2. You see what I mean? Okay? So like if I were to draw, for example, let's say I move that like these, if I did this one, and I just moved this group right here, and say now I moved it over to that carbon here. That's not a new structure. Okay, it's the same thing, it's just a mirror image. Okay, so that doesn't work because I've already drawn it. Does that make sense? Okay, you can't draw a mirror image of it. That's the same structure. It's the same structure. Okay, that's not it. It doesn't count as an isomer. Yeah.
Are you saying the first you crossed out is not correct in general, or it's just not new?
It's not a new one. Yeah, it's not a new one. Right, because well, actually, it's really the same as this one right here. It's the same thing. All I did was like, because remember the bond angles. If we made the molecule and we like drew it out, the bond angles from here, there's 4 things that are attached to it, right? They're all 109.5, but I just have on one of those angles, I got a carbon coming out. If I twisted it, the carbon would move up into a different spot, but it's still the same molecule because you can rotate them around however you want, but it gets a little funky when it comes to that. But like, for example, this might illustrate it better when we're just looking at the chlorine here. So if I were to draw an isomer of this, right, what I'm going to do is I'll move that chlorine, right? Okay, I'm not going to draw in the other hydrogens. Right? All I do is move that chlorine to that carbon. Okay, that works. Now, what if I move that chlorine to the other carbon? It's the same thing. It's equivalent. It's the same structure. It's not a new isomer. That makes sense? Okay, because it's just a mirror image of it. It's an equivalent structure. There's really only one other isomer there. So if we go down, we do a couple more here. So you can start drawing a bunch of these as long as they're the same formula and you're moving things around a little bit. So I might draw one that's like C with the H's here. It's still C3 H 1, 2, 3, 4, 5, 6 O2, right? or we just move things around a little. As long as it is the same formula, we can move something around. So maybe we can try, what if we did this one? There we go, that's another one. Still C3H8 or H6O2. Okay, so it's the same formula, different structure. Okay, so for like the next one, let's draw a couple of these here. I'm drawing draw 2 experts for that one there. We'll see if we got a. All right, so that's one that I drew. Let me draw another one. Anything else? What else did you guys come up with?
I just have a question. So, like the carbon, since I know like the least electromagnetic has to like be in the middle, you couldn't move the carbon on the outside, could you? Like, because they have to stay at the core of the.
We're not really worried about this for right now with the, like for when you're doing a Vesper molecule and there's only one center atom, that's the case. Okay, this is for like, hey, here's a structure, draw a bunch of other ones that are different from that one.
So, like you're saying, put the Cl in place of a carbon?
There's a problem in doing that though. Like the chlorine will only form one bond, right, in this case. So just move the chlorines around. Yeah, keep the chlorine on the outside. Yes, yeah. Yeah. And I suppose if you wanted to, you could start bonding with chlorine because it's got extra valence electrons and stuff. As long as your, yes, as long as your structure works, you just keep drawing, right? So like same thing with this one down here. You can just start moving things around. Yeah, you just start moving stuff around. All right, so an isomer is just same formula, different structure. Okay? All right. So next thing here, this one is talking about bond dissociation energy. All right, now this one is a little, couple things to be aware of here. In order to break a bond, you got to put in some energy. All right. But also, if breaking bonds, in some respect, it does release energy as well. Okay. So, but to break bonds, sometimes you got to remember you need that little push of energy, activation energy, and stuff like that as well. But ultimately, what we can do is we can calculate the overall net charge when a reaction happens. But something that I want to point out to you here that's slightly different than what we've done so far is when we're looking at bond energies, we are looking at reactants minus products. Remember when we calculated enthalpy values, it was products minus reactants. In this case, when we're looking at bond energies, okay, or bond dissociation energy, it's going to be reactants minus products. All right, so this is called the broken law, called that because it's backwards of what it should be. Every other, when we do delta S, delta G, delta H of reactions, and this is for bond energy, when we do for reactions and stuff, it's always products minus reactants. Always products minus reactants. This is the only case where it's reactants minus products, is when you're talking about bond dissociation energy, bond energy. Okay, so that's the key here. So the reason why that's the case, it's some because of this right here. Some of the energies required to break old bonds, plus the sum of the energies released for new bonds. Okay, so that's why it's going to be reactants minus products. All right, so you're going to always be given values. All right, this is just coming right out of your book. This table, and it's always in kilojoules per mole. All right. Now, if we compare, so it's some interesting trends to look at here a little bit. And one of them gets at the first question that you're looking at, all right, which has a larger bond dissociation energy, a double bond or a triple bond? Well, let's just take a look at, we looked at carbon-carbon double bond and a carbon-carbon triple bond. All right, which has a larger bond, which takes more energy to break? Triple bond. That makes sense, right? Okay. Triple bonds are stronger. It's going to require more energy to break those, release that energy. Okay. So triple bond. All right. Another trend you might want to check out. This is kind of interesting. Notice these guys right here. As we move down a group, right? Fluorine, chlorine, bromine, iodine. What changes about those? About fluorine, chlorine, bromine, iodine as we move down the group? Because these are all single bonds to carbon, but as we move down the group, what's changing? Stop. What goes up? As we move down the group? Yeah, from F to Cl to R to I. Yep. The energy?
159, 193, 212. Am I looking at the wrong thing?
I'm right here.
Oh, I'm in a different.
Oh, okay. There we go. All right. Yeah, it's going down. Okay, great. Why does the energy go down? Because the distance increases between the two atoms. Because the radius keeps getting larger and larger as you move down the periodic table. So as distance increases, the force of attraction holding them together is less. So it takes less energy to break the bond. Okay? All right. What's that? Yeah, just like magnets. Okay? Further the magnet is from the other one, it's your pull part. Okay? All right, so let's do a few calculations here. So on the next page here. So this was the one you were looking at. Is this the table you were looking at or no? So when we do this, remember it's always reciprocal law, so it's reactants minus products here. Okay, so for H2, we've got 432. So delta H is equal to 432, right? Plus our 154 from the fluorine minus our products. Okay, products we have 565 kilojoules per mole associated with that bond and with that HF bond. But how many HF bonds are we forming here? 2. So we have to multiply that guy by 2. All right, so in that case, the 2 is coming from the balanced equation. So we pull out the calculator. $32 plus 154, 586 kilojoules per mole, minus 2 times 565, 130. So it's equal to 586 minus negative 544. Okay. There we go. All right. Okay, so let's take a look at the next reaction here. So you've got methane burning. So something I want to do here, I'm going to kind of do this. So what's the Lewis dot structure for methane? What's the Vesper shape for methane? Tetrahedral. Yeah, because it's CH4, right? So we've got all right, here's methane's Lewis dot structure. And we also have O2. So here's the Lewis dot structure for O2. We got 2 of those guys going to CO2. All right, if we draw the Lewis dot structure for CO2, I'll help you to draw these sometimes. CO2 and H2O. We have 2 H2O molecules there as well. All right, so when we go reactants minus products here, how many CH4 bonds do I have to break? I got 4 of them. Okay, so there are 4 CH4 bonds. So CH4, if I go back up to my table here, here's CH4, 413. So I got 4 times 413 plus, right? So that 4, just I'm going to make sure to point that out to you. 1, 2, 3, and 4, right? Because of those 4 bonds there. That's where that 4 is coming from. And then we got 2 times O2, which is, O2's right here. So 498. All right, so there is, that's the reactants. And for the products, right, we've got 2 times CO2. We got 2 times, oh, and there's a special energy for CO2, 799. 2 times 799, because we got 2 bonds. All right, we got 2 C double bonded O's. Okay, so that's where that 2 is coming from. And then finally here we've got water. We only have H and O bonds, but how many total HO bonds? We got 4. Yeah, because for each water molecule there's 2. So we've got these 2 times these 2. Okay, so you got a total of 4 times then H and O. Where's it at? Here it is. 467. Okay, so all the way. That's where that's coming from. 2 times 2. Got 4. So if we crank this out, we have negative 818 kilojoules per mole. It isn't. It's heat's being released. Yeah, it's negative. Yes.
You just count up the number of bonds, regardless what type of bond it is, like double bond. You just count them.
Yeah, you just look it up. Like you just look up the value for that particular bond and then find, okay, how many of those do I have completely? You know, like if I had a, let's say there was a 2 in front of CO2, I'd have a 4 here.
Okay.
You know what I mean? Like if there's a 2 here, that means I got 2 CO2 molecules, which means I got a 4 C double bonded O bonds to look at.
Mm-hmm. And we're gonna get this chart, right?
Oh yeah, you'll be given those values. More than likely, the problem will look a lot like this number 2 here, where they give you the values. Here's the reaction. Okay, go. Rather than giving you the whole kit and caboodle table up there. All right. No. But you got to know the Vesper chart for the quiz. But for the quiz, most of the Vesper stuff on the quiz is like really pretty common stuff. Quiz is tomorrow. What happened to my? It's the hard way.